Okay, in 8.3, we were talking about graphing reciprocal functions. Now in 8.4, we will be graphing rational functions. And rational functions have a variable both on the top and on the bottom. Rational functions can have three different kinds of asymptotes. They can have vertical and horizontal asymptotes, just like our reciprocal functions, but they also have the possibility of having an oblique asymptote, which is a slant asymptote. For vertical asymptote, that vertical asymptote happens whenever whatever's going to make that bottom equal to 0. It's the easiest of all three asymptotes to remember because you just need to factor the bottom and set it equal to 0, and that gives you your vertical asymptotes. The horizontal asymptotes, there can either be a horizontal asymptote equal to 0, no horizontal asymptote, or a horizontal asymptote that's equal to the leading coefficient of the top and the bottom over the bottom. And it all depends on what the degree of the top and the degree of the bottom are. So if the degree is bigger on top than it is on the bottom, and remember the degree is the largest exponent, so if it's bigger on top than it is on the bottom, then there's not going to be a horizontal asymptote, but we'll have to check for an oblique one. If the degree is smaller on top than it is on the bottom, then our horizontal asymptote is at y equals 0. Finally, if we have a degree that's the same on top as it is on the bottom, then you're going to want to take your leading coefficient of the top and put it over the leading coefficient of the bottom. Just a reminder that your leading coefficient is the number that's found in front of the term where your degree was. Now, an oblique asymptote only happens if the degree on top is exactly 1 bigger than the degree on the bottom. So if I had x to the third on top and x squared on the bottom, then I've got an oblique asymptote happening. How we find an oblique asymptote is we use our polynomial division. That's the box method or synthetic division, if it's okay. And we divide the top by the bottom, and we ignore any remainder that's there. So your answer is the equation for y equals whatever you got when you divided. And we'll do one or two of those so that we can see what they look like. Finally, there's a chance that there's some point discontinuity. Point discontinuity is what we call a hole in the graph. And these happen whenever you factor the top and factor the bottom and those factors cancel. The canceled factor creates a hole in the denominator. Remember at the beginning of the chapter I told you that we can't just ignore the fact that something canceled. That's where that comes into play. If something canceled, at that point, there would be a point of discontinuity, and we would use an open circle to represent a hole in the graph. Let's take a look at some examples for 8.4. So we're going to graph each function and we're going to state the domain and range. Now these don't have h and k values like the reciprocal functions did. A reciprocal function only has a number on top, no variable. Rational functions have variables on top and bottom, so they follow a little bit different rules. Your first step with these is to identify what's the degree on top and what's the degree on the bottom. So in this first example, the degree on top is 2. The degree on the bottom is 2, because remember that's the highest exponent. And those two are equal to each other. So if we look back at the horizontal asymptote rules, we see that there's a horizontal asymptote when they're equal to each other of y equals your leading coefficient of the top, which is 1, over the leading coefficient of the bottom, which is 1. 1 over 1, or just 1. For your vertical asymptote happens at x equals whatever's going to make this denominator equal to 0. In order to find that, you need to actually factor out the top and factor out the bottom. X plus 1, x minus 1. So we're going to have two vertical asymptotes because there are two numbers that would make the denominator equal to 0. 1 and -1. Now, if there is any kind of horizontal asymptote, there can't be an oblique one. Remember, an oblique only happens if the degree on top is 1 larger than the degree on the bottom. So these are our only asymptotes, 2 vertical and 1 horizontal. Your domain and range comes from your asymptotes, or the holes that we'll see later. The domain is all real numbers except it can't be 1 and it can't be -1 because there's asymptotes happening there. Your range is all real numbers except your horizontal asymptote, which is 1. So the first thing that you're going to do is you're going to plot these on your graph. Now, I might actually recommend to you, especially when we get into the oblique asymptotes, that you type it into your graph first, because some of these you're going to want to change what the scale is. So I have x squared minus 2, and you're going to want to put that in parentheses, because remember, we want the whole top in parentheses over x squared over, x squared minus 1. So I've got the top in parentheses, I've got the bottom in parentheses. And then take a look at the graph. Because our graph, I still have a weird window happening. Our graph only goes from -5 to 5 approximately. So we want to make sure that we would be able to see that on our graph. And it looks like we would be able to see that. There's nothing super weird or anything of that nature. So let's take a look here. We're going to graph at x equals 1. And -1. And then we've got one at y equals 1. Now, actually, I just realized our domain and range is going to be just a smidge off. Our domain is fine, but our range is actually going to change just a little bit. And I'll explain about it in just 1 second. So let's go to our table, and we're going to pull some points from it. So we can see our two asymptotes happening here. So I'm going to pull something from all parts of the asymptote. So at -2, it's at 0.6 repeating. We've got one at -3, it's at 0.8 repeating. So we can see that our hyperbola is going to look something like that. The only point happening in between here is a 2. And then the other side, I have one at 2 and 0.6 repeating, 2 or 3 and 0.8 repeating, and so on. So our hyperbola is going to go right along, never touching or crossing the asymptotes, just like the reciprocal. Let's take a look at this middle one, because that's what's going to cause the hiccup in our domain, our range as well. If you look at the graph, you'll see that in the middle, it's got a U shape. Now, our table isn't able to find that, and frankly, I'm okay because it's such a small space in here that you plot just the point that was in between there, and then plot the rest, or estimate the rest of it. But there's a reason why our range is not just that y can't equal 1. Our range is that y is going to go up to 1, and that's evidenced by the bottom two branches that we plotted. But also, it skips from that asymptote at 1, it skips all the way up to that U shape at 2. So we need to make sure that we know the minimum value of that U shape. We can't be sure that it's exactly 2 because we don't have any other points to base our knowledge off of. So you need to use your minimum calculating tool. Second, calc, minimum. And we're going to go to the left side and the right side, just like we did with parabolas. And just double check that, yes, it is in fact 2, the minimum value. So that means our range, we've got a couple of different inequalities to write. We have that y can be less than 1, as evidence, like we said, of these two branches. But then it skips up and it says that y is greater than 2 or equal to. Now the reason why it can be equal to is because we actually got that point at 2. And it can't be equal to the 1 because that is exactly where the asymptote is. So we have to list both parts for our range. Let's take a look at the next one. For the next one, we're going to list our degree of the top, degree of the bottom. The degree of the top is bigger than the degree of the bottom, which indicates that there is no horizontal asymptote. Then we need to identify our vertical asymptotes. So we need to factor the bottom, which x plus 2 cannot be factored, and identify what's going to make it equal to 0. So what would make x plus 2 equal to 0 is if x was negative 2. So we're going to have an asymptote at x equals negative 2. We also don't have an oblique asymptote here because the degree on top is more than just 1 bigger than the degree on the bottom. So we have x to the third divided by x plus 2. Remember to put our top and our bottom in parentheses and graph. Now we've got a vertical asymptote happening at x is equal to negative 2. But I want to make sure that I'm not seeing other parts of this because when I look at the table, you'll see at negative 2, there's our asymptote. I've got points that are continuing below that asymptote, but I don't see those points plotted on my graph. So I need to actually change my window to include some of these points. 27, 32, 41. So we need to change our window so that our maximum goes up to something that will include those points. And we'll see that there's been a missing part of that branch happening all along. That also indicates that we need to change our window here so that we can see those points as well. So I'm going to choose to count by tens for my y's. So that I can see all of those points. Here's a little expert tip for you. If you plot the scale on the graph to be the same scale as your calculator, you'll get a really good picture of what your paper should look like. So I want my x's to go from negative 5 all the way up to 5. and they counted by ones. And I might want my y's to go from negative 50 all the way up to 50, and they counted by tens. So now when I hit the graph mark, this is exactly what mine should look like when I'm done plotting. So I have x is equal to negative 2 as my asymptote. And then I can plot some points. So at negative 5, it's at 41.6 repeating. Negative 4, it's at 32. And then negative 3, it's at 27. At negative 1, it's at negative 1. Then 0. Then 0.3. And I can scroll all the way down to get some bigger numbers here. At 5, it's at 17. So if we looked at our graph, we can see that this went along the asymptote. And over here came down and along the asymptote. So my domain is still all real numbers except negative 2. That's the only thing that x can't be. Oops, sorry. All real numbers except negative 2. And then our range, it goes all the way off the graph below, and this branch takes it all the way above. So our range is actually all real numbers. All right, I know that that's kind of difficult to see. Hopefully you can see that a little bit better. There you go. Let's take a look at our last one on the first line. Degree of the numerator is 2. Degree of the denominator is 1. Degree on top is bigger, so that means there's no vertical asymptote, but we need to check for an oblique. An oblique, member, only happens if the degree on top is exactly 1 on the bottom, which is what we have here. So we need to do some polynomial division. I have one term that I'm dividing by. So if I take x out of 6x squared, I have 6x. X out of negative 3x, I have negative 3. And I can't really take x out of 2. And so that would be my remainder. So y equals 6x minus 3 is my oblique asymptote. My vertical asymptote happens where whatever's going to make the denominator equal to 0. So let's type this into our calculator, see what the graph looks like. You might want to hit zoom 6 to be able to go back to a nice normal window. And we're going to type this into our calculator. So our nice normal window is at negative 5 to 5, or negative 10 to 10 on our graph. But our calculator only goes from negative 5 to 5. Or our paper only goes from negative 5 to 5. If you take a look at your window, or your table, we can see that I've got some other values here at negative 1 that I'm not including if I just go counting by ones. So I need to change those values to be something bigger, like negative 40 or negative 50. And if I made my x's count by -5 to 5, so our same window that we had before, I can now see that there's actually 2 branches of this graph. Now don't be fooled. This actually doesn't stop like my calculator indicates. It looks like it stops at 2 and stops at, or -3 and then stops at 2 point something. What that's actually doing is it's just getting so close that it can't show you that it's going along that asymptote. On your paper, it should go along the asymptote and should not stop. So we're going to have 2 very odd looking pictures here. So first label your tick marks. I got both branches of the graph when I did -10 or -5 to 5 for x's, counting by ones. And then label your y's to count by tens. So we know that we have an asymptote happening at x equals 0. But we also have this asymptote happening at 6x minus 3. So we'll graph that asymptote first. Because we have such a strange window here, it can be difficult to graph that by just using your slope and your y-intercept. So my recommendation to you is to actually graph it on your calculator and get some points that will match what we've got going on here. 6x minus 3. And if you highlight the equal sign next to where we were before, we can get your calculator to not have that graphed. So we're going to go to our table and plot some points. So at -1, my table says that it's at -9. At 0, it's at -3. At 2, it's at 15. At 4, it's at 21. At -2, it's at -15. At -4, it's at -27. So now I've got a good idea of what my asymptote looks like. So my asymptotes make this X shape. So you can go back to your calculator and clear out our asymptote. So we need some points. We need some points to plot on there. So we're going to go to our y equals, or then go to our table. And we're going to plot some points on here. So at -6, at -6, we're at -39, which is kind of off our graph here. So -5, we have -33, -4 is at -27, -3 is at -21. See, those are running just right along that asymptote. -2 is at 16. -1 is at -11. And then it runs just along that asymptote. The positive side, we have 1 is at 5, 2 is at 10, 3 is at 15, 4 is at 21.5, and it's running right along, but never touching or crossing that asymptote. Okay, and you'll remember when you graphed it, it got really, really, really close. And it was almost like it was going to touch or cross because it got so close. So be very careful when you're plotting them. For domain, it goes to the left forever, goes to the right forever, and it seems to only skip that vertical asymptote. So our domain is all real numbers except 0. Now our range, it goes down forever thanks to this branch, but it goes up to this unknown point. So we need to find that unknown point by calculating our maximum. So left side of the maximum, right side of the maximum. Maximum happens at negative 0.57 for the x, and we care more about the y value because we're looking for the range. So y is less than or equal to negative 9.93. And now it skips. After that point, it skips up to this value, which is a minimum value. So second calc, minimum. You're going to go to the left side of it, to the right side of it, and calculate. And it's happening at 3.93. So y is greater than or equal to 3.93. The oblique asymptotes are probably one of the most complicated graphs that we'll do this year. Well, not probably. They are the most complicated graph that you'll do this year. So don't get discouraged. They just take some practice. Let's take a look. Got 2 more graphs here before we'll head into the word problem. All right, so the degree on top is 2. The degree on the bottom is 1. Remember, those are just the highest exponents. Oh, I guess I can zoom out a little. The degree on top is bigger than the degree on the bottom, so that means there is no horizontal asymptote, but we need to check to see if there's an oblique. And there is an oblique asymptote because the degree on top is 1 larger than the degree on the bottom. So we're going to need to do polynomial division. So we have x plus 2. Bringing back all of our stuff at the end of the year. So this is from chapter 5, 5.2. We have x squared. X times what is x squared? X. X times 2, 2x. 2x plus what is 8x? 6x. X times what is 6x? 6. 6 times 2 is 12. 12 plus what is 20? X times what is 8? That doesn't really work. So that's our remainder. Remember, we get to ignore our remainder. So y equals x plus 6 is our oblique asymptote. Now, for our vertical asymptote, it's whatever is going to make the denominator equal to 0. And in that case, it's x equals negative 2. So let's take a look at our graph on our calculator. Clear out our graph from before. x, parentheses, x squared plus 8x plus 20 divided by x plus 2. And we're going to graph it. Just take a look at what it looks like. Oh, remember we've got that really weird window. So we're going to want to change our window back to our normal window. Zoom 6. Okay. And when I do that, I can see, oh, it looks like there's just a little bitty branch hanging out to the side here. So let's take a look at our table and confirm that. So here is our vertical asymptote at x equals -2. And on either side here, you can see, yes, there is just a little bit that's hanging off of there, but I think we could probably get away with not having, not counting by something other than ones in this case. So we're going to plot our asymptotes at -2, x equals -2. And then y equals x plus 6. You can plot it with your calculator if you want, or you can use our trusty old slope and y-intercept form. So the y-intercept is 6, up 1 over 1 for the slope. So looking at where we're going to plot our points here. So I've got -3. It's at -5. 1, 2, 3, 4, 5. -4 is at -2. -5 is at -1.6 repeating. And 6 is at -2. 7 is at -2.6. So we can kind of get an idea here of what it looks like. Now, you can see here that there's a maximum value that happened. So I might want to go back to my graph here and go ahead and calculate that maximum value, because it's going to matter with my domain and range. Now, notice I don't see my cursor anywhere on here, and that's because it's plotting at x is equal to -0.9, which is off of my graph. So just keep pressing your left arrow until your cursor pops back up. So here's our cursor. We're going to go to the left side, to the right side, and we have a maximum value at -234.8, -1.65. So I went a little high, but that's okay. So that means that my range, my y, is going to be less than or equal to -1.66. Then let's pull some other points from the other side. At -1, it's at 13, which is way off my graph. 1, 2, 3. It's like somewhere in this neighborhood. At 0, it's at 10. And then at 1, it's at 9.6 repeating. Then again at 10, 10.6. So we can kind of get an idea of what this looks like. And we want to calculate that maximum or that minimum value. So again, right arrow key until we can kind of see the minimum or see it pop up on there. Okay, so 0. And that minimum value happens at 9.66. So y is greater than or equal to 9.66. Now, the last one is something that we need to take a look at. Now, in letter C and letter D, if we would have attempted to factor the top of either of those, we would have realized that they weren't factorable. However, remember your first step pretty much with anything in this chapter is always to factor first. So we're going to take a look at E and try and factor E. So take a moment, use your A times C in your box to factor out what E is. And if we factored out E, we would get x plus 4 and x minus 3. Now you'll notice that in our simplifying sections in 8.1, we would have said, oh my goodness, x plus 4 is on top and it's on the bottom. It cancels. So it simplifies down to just x minus 3, which is true, but we cannot discount the fact that x plus 4 was on the bottom at some point in time. So instead, we call that a hole. It's not an asymptote. It's a hole, and that hole happens at whatever's going to make that denominator equal to 0. So in this case, negative 4. So there's a hole at negative 4. And once I've found the hole, then I can take a look and say, okay, yes, it's simplified down to x minus 3, which is no longer a rational equation. So it doesn't have any asymptotes. It doesn't have we don't have to worry about obliques. We don't have to worry about vertical or horizontal or degrees or anything like that. It's just a nice, simple graph, with the only exception being when we get to x is equal to negative 4, we're going to need to put an open dot there. So let's go ahead and graph x minus 3. So that's a slope of 1 and a y-intercept of negative 3. So down 3 and put a dot, up 1, right 1. Again, you can use your calculator if you want to graph it. And left. Here's negative 4. So we use an open dot here to represent that there's a hole. So when I draw my line for the rest of the graph, we use our solid line, but at that one point, we use an open dot to represent that there's a hole in the graph. Now, if you were to type the original equation into your calculator will not show you the hole on the graph anyway. In fact, it will just look like a straight line. However, if you looked at the table, you would see the error happening at the hole. So we need to represent that there is an error happening at the hole. Do not be fooled by just plotting what you see. You need to know what that looks like. So your domain, all real numbers except that problem child, that negative 4. And the range, all real numbers except, what is the y value here? It's at negative 1, 2, 3, 4, 5, 6, 7. All right, we have a word problem to work through now. Eduardo is a kicker for his high school football team. And so far this season, he has made 7 out of 11 field goals. He would like to improve his field goal percentage. If he can make X consecutive field goals, his field goal percentage would be determined by this graph. So first it's asking us to graph the function. Before we graph this function, I want you to think, what would make sense in terms of graphing this? So X is the number of consecutive field goals that he makes. Obviously, that has to be a positive number because we can't have a negative amount of field goals. And then the P of X, that represents his field goal percentage. And you can't have a negative field goal percentage either. So therefore, the only part that would make sense in the context of this problem is things that are in the first quadrant. So when I graph this, I'm only going to use the first quadrant to graph. Now, when we take a look at this, we need to identify all of our asymptotes. We have the degree on top is 1, the degree on the bottom is 1. When the degrees are equal, we need to look at their leading coefficients for our horizontal asymptotes. So in this case, the leading coefficient of each of these would both be 1. So at y equals 1, there's an asymptote. There's a vertical asymptote happening at whatever's going to make the denominator equal to 0. So at negative 11, if x was negative 11, that would make this denominator equal to 0. So there's a vertical asymptote happening at x equals negative 11. Now, negative 11 does not fall in the first quadrant, so it's not going to show up on our graph of the first quadrant. There's no oblique because the degree on top is not 1 bigger than the degree on the bottom. So when we graph this, take a look at your calculator so that you can determine what would be a good window to use for this. So you have 7 plus x divided by 11 plus x. Now we've already determined that we're only going to be looking at this first quadrant. And this first quadrant, man, that graph looks awfully low. It might be very challenging for us to graph that in that spot because it's so close to 0. They're all very close together. So I suggest perhaps changing our window so that the y value goes only up to 1. And maybe it counts by tenths instead. Now we don't need all of this down here, so we can take that all out as well. So we don't need all the negatives. We don't need the negative for y either. So now it looks closer to like what I'm going to see on my quadrants, on my single first quadrant. So I'm going to count by 0.1s. So I have our asymptote happening at y equals 1. And so let's get some points here. At 1, it's at 0.6 repeating. At 2, it's at 6.9. 5, it's at 7.5. 8, it's at 7.89. All the way at 10, it's at 8.1. So it's going to slowly, gradually get closer and closer and closer to that 0, but never or to that asymptote, but never actually touch or cross the asymptote. Now the second part of this is asking me to describe the meaning of the intercept of the vertical axis. So that was at 0.64 according to the calculator. So that would mean at 0 consecutive field goals, because remember this is his field goal percentage. This is his number of field goals. So at 0, if he makes no more field goals, he doesn't make any more attempts or anything of that nature, that represents his current field goal percentage. Now the equation for our horizontal asymptote, we decided that it was at y equals 1, and that it would be, the meaning of it with respect to his field goal percentage is that this is at 100%. If he had never missed a field goal in the first place, then his field goal percentage would be 100%. But it's acting as an asymptote because he's already missed field goals. He's already missed 4 field goals. So there's no way that his field goal percentage can ever be 100%. It'll get really, really, really close. If he makes 100 field goals in a row, it'll get really, really close to 100%, but it will never actually touch 100% or go above 100%. So the horizontal asymptote represents 100% field goal percentage, which you can't get because he's already missed 4 field goals.